Okay, in this lecture, we're going to do probably a little bit of a review, and also probably go into a little bit more detail than you've gone before, into the concept of catalysis. So, starting with the definition of a catalyst. So, we probably have heard the definition, for example, in our chemistry classes, that a catalyst is a material that accelerates the rate of a chemical reaction without being consumed. In reality, a catalyst that's a good catalyst that does that. A catalyst doesn't have to accelerate the rate of a reaction. What a catalyst does is it provides a different pathway from reactants to products than would happen in the absence of the catalyst. And so a good catalyst would provide a lower energy route from reactants to products. We tend to classify, or another way to think about a catalyst, so in this class we talk about reactive intermediates. So a catalyst is a reactive intermediate that promotes production of a large number of product molecules. And that is probably the most general definition of a catalyst. And again, that's a good catalyst. So if it's promoting production of a large number of product molecules, it's doing a good job. So another thing catalysts do, they provide lower energy routes from reactants to products without being consumed themselves. Again, that is a good catalyst that does that. So some concepts about catalysts. Catalysts influence the kinetics, but they do not influence the thermodynamics. At least not the thermodynamics of the overall reaction. They do indeed influence the thermodynamics of individual steps along the new pathway, but they do not influence the thermodynamics of the overall reaction. In fact, they can't. So this is one of the concepts of reaction energies, or energy being a state function. So enthalpy, for example, if we think about a heat of reaction or a free energy of reaction, these are state functions. That means that those quantities, the free energy of reaction or the enthalpy of reaction, only depend on the reactants and products. So how we get from reactants to products doesn't matter in the calculation of those quantities. The catalyst is affecting what goes on in between reactants and products, but it's not affecting the reactants or products. So it doesn't affect the thermodynamics, but it can affect the kinetics. It can bring down the activation energy. So let's kind of illustrate that. There are two types of catalysts. There are both homogeneous catalysts and heterogeneous catalysts. Homogeneous catalysts are in the same phase as the reaction fluids. Heterogeneous catalysts, the catalyst is in a different phase than the reaction fluids. The operation of catalysts is similar amongst the two, although we'll see some differences in the way that we write notation. So some examples of homogeneous catalysts, these would be ion or acid catalysts. For example, if you have something with a solvated proton and the proton helps to promote the reaction. Organometallic catalysts, these would be essentially metal cations that have a ligand environment around them and maybe are dissolved in some type of solution. Also enzymes, which are typically contained within proteins. Those typically would exist in an aqueous solution along with a species that they would react with. Another example is the catalyzing of the decomposition of ozone with chlorine atoms. So this goes on in the atmosphere. So this is a gas phase reaction. So we'd have gas phase chlorine atoms participating in the decomposition of gas phase ozone. So in the absence of chlorine, the way that ozone decomposes is by reacting with gas phase oxygen atoms. So you see these are chlorine atoms, oxygen atoms. These are not highly stable species, but in certain parts of the atmosphere they exist, at least in small concentrations. So for this reaction to happen, there's an activation energy associated with it. The activation energy in this case is 20 kilojoules per mole. What the chlorine atoms do is to lower that activation barrier. And they do this in two steps. This is a two-step mechanism. We'll say two-step mechanism. So the chlorine atom will react with an ozone molecule, forming O2 and this, what is this? I don't even know how to name that thing. Chlorine oxide. This has an activation energy of 1 kilojoule per mole, so significantly lower. This chlorine oxide can then react with oxygen to form O2 and chlorine. This has an activation energy of 2 kilojoules per mole. Let's say these are activation energies. We also refer to them sometimes as delta E act. So you see here what's happened. The chlorine atom is regenerated. So it's not created or it's not generated or consumed in net. So if I were to sum these reactions, then I would get O plus O3 goes to 2O2. Same reaction as right here. Same overall thermodynamics. That means that the reaction energy is the same. However, instead of this reaction happening in a one-step process with a higher activation barrier, this reaction now happens in a two-step process where both reactions have significantly lower reaction barriers. You notice that the chlorine cancels out, so the chlorine here is the catalyst. And it's not part of the overall reaction. This chlorine oxide is an intermediate. We'll say a reaction intermediate. And it's also not part of the overall reaction. So when you write out a mechanism like this, there's those two requirements. The catalyst should cancel out, which we show it doing here and here. Also, any reaction intermediates should cancel out, which we show them doing here and here. Okay, so basically what we have the same reaction. But the kinetic pathway is more favorable. And that's because the highest energy barrier that has to be surpassed in the catalyzed reaction is 2 kilojoules per mole, whereas it is 20 kilojoules per mole in the absence of that chlorine catalyst. So we can draw that out. So if I draw an energy diagram, here I have energy. And I'm not going to draw it to scale, so I'm not going to provide units, but we know the values of the activation energies. So this is my 0 line. So if I make my reference state be my reactant species, that means the energy of my reactant species is 0, or the relative energy is. And then let me attempt to draw this here. something like this. This is going to be my oxygen plus ozone. This is going to be 2O2. This is my reactions in the absence of chlorine, and I have an activation energy here. 20 kilojoules per mole. If I have the chlorine, I'll make this a different color. Maybe I should make it a completely different color to not confuse with the colors I used above. Now I have two steps, and that's already terribly drawn. Man, I'm just not doing that well, so let me see if I can try it one more time. Still not really great drawn. And again, not to scale, but this is going to be in the presence of chlorine. This is going to be 1 kilojoules per mole, and as you can see, this is not drawn to scale. Just trying to illustrate here. So not drawn to scale. Doing my best here. Okay, so anyways, now we have two steps, each with an activation barrier. Those are illustrated in this diagram. Both of those activation barriers are smaller than the case where chlorine was not present. And let me label this here. We'll call this reaction coordinate. Reaction coordinate is kind of a complicated term, but you can think about it as the geometric structure of everything as it goes from oxygen and O3 to 2 oxygen molecules. We'll get into that a little bit more towards the end of the class, or at least provide some illustrations. So as you can see here, these two concepts, the catalyst provides a lower energy pathway from reactants to products. Also, it alters the kinetics. So the observed activation barrier for the catalyzed case would probably be 2 kilojoules per mole. So in the uncatalyzed case, it was 20. So it's altering the kinetics. But it does not alter the thermodynamics. So we go back to this energy diagram. The reaction energy is this value. We'll call it delta H of a reaction. And we could argue there about the precise quantity of what that is, but let's use heat of reaction since it's familiar to us. And you could argue with me and tell me that that's not correct, and you would be right, but for all intents and purposes, it's a fine quantity to use there. As we see, this reaction that quantity, the reaction to the heat of reaction, the reaction energy does not change whether or not there is a catalyst there, because it doesn't matter. All you're going to do to get that value is take the relative energy of the products, or the energy of the products relative to the reactants. That has nothing to do what goes on, and this is because delta H of reaction, delta G of reaction, etc. These are state functions. In other words, the path doesn't matter. The only things that matter are the initial and final states. Okay, let's talk now about heterogeneous catalysts. So, differences between heterogeneous and homogeneous catalysts. Homogeneous catalysts tend to be more precise, so they will carry out very precise reactions. Not always. However, they can also be pretty difficult to separate out, for example. Heterogeneous catalyst is in a completely different phase, probably requires no separation. Problem with heterogeneous catalyst is that it likes to promote a lot of reactions, so it can be hard to get selectivity with heterogeneous catalysts. Anyways, maybe a fun fact for you since you're a chemical engineer. Heterogeneous catalysts, different phase than reaction fluids. Typically solid. Whereas reaction fluids be liquid or gas. So some examples, supported metal catalyst, very common. Chances are you have one of those in your car. The catalytic converter is typically made out of a ceria zirconia type support with metals such as platinum, rhodium, palladium. Very typical catalyst. Research-wise, it's going to be a platinum supported on alumina. Another type of very common catalyst is a zeolite, otherwise known as a molecular sieve. This is a porous catalyst. It's used for a variety of things. Zeolites are typically porous silica comprising materials. However, silica can be exchanged for other types of cations, and if there's a charge imbalance, that leads to protons within the structure. Those can serve as, for example, Bronsted acid sites. Another type of common catalyst is the Ziegler-Natta catalyst. This is kind of like a homogeneous catalyst. In this case, we have like kind of a organometallic complex. We have a titanium chloride complex. But instead of being dissolved in solution, as would be the case in a homogeneous case, it would be anchored, in this case, to a magnesium chloride solid surface. So lots of different types of homogeneous catalysts. Those are some of the ones that are used a lot in both industry and in research. So how does this work? I'm going to draw this again using an energy diagram. Let me zoom out just a little bit. So I have my energy axis, and this is going to be my reaction coordinate. And again, I'll draw my zero line. Energy equals 0 here. So let's look at the example of carbon monoxide oxidation on platinum alumina. So this reaction looks like is we have 2CO gas plus O2 gas goes to 2CO2 gas. And this is going to happen. We're going to look at the case in the homogeneous case versus the case where this reaction is carried out over a platinum catalyst. So in the homogeneous case, it's not well drawn. Again, we're going to set, like in the last example, we're going to set the reactants as the reference state. So this is going to be so that energy is going to be equal to 0. I didn't draw any of that really well, so let me quickly. I can just erase that. Okay, we'll say 2CO gas plus O2 gas. That's there. At the transition state here, what I have is carbon monoxide gas plus oxygen gas. So we can actually estimate what this barrier is, because we know the atomization energy of molecular oxygen. We can look that up, for example, on the NIST website. For this reaction to happen, an oxygen molecule is basically going to have to come apart. There's nothing to help it come apart, so it just has to come apart, right? So probably the temperature has to be turned up hot enough that as this thing is like vibrating, that it vibrates so fast that it like splits. It's a lot of energy. That's why the activation energy is so high. That's the gas phase. The surface phase reaction basically looks something like this. It goes down originally, then goes back up, goes down a little bit, and then back up. And these lines are meant to be smooth and not have shoulders. I'm just not very good at drawing. Here, what we have is adsorbed CO and adsorbed oxygen. So when I write these asterisks here, that's indicating a site on the catalyst surface. So you can think about that as being a platinum atom on the surface. So in this case, we have two CO bound to 2 platinum. Actually, let me write that a little differently. 2 CO, this is a parenthesis. Here we have a transition state. Oops. We often might denote this using the dagger symbol. This is forming the oxygen carbon monoxide bond, or forming one of those. And it makes me realize too that I have a error in my stoichiometry over here. Okay. Here we're going to have adsorbed CO. I'm sorry, adsorbed CO2, and we'll have 2 of those. This is a parenthesis. And then here we have 2 CO2 gas. Actually, I can write that. Let me write that in black ink because it's part of the thermodynamics. So what happens in this pathway, carbon monoxide and oxygen adsorb to the catalyst here, so they bind to the catalyst. So they come out of there, they're whizzing around in the gas phase, they collide with this platinum catalyst, and they become stuck to it. They're bound. The oxygen additionally dissociates, so where we have oxygen molecules in the gas phase, we have oxygen atoms on the surface. These 2 things then combine, going over this transition barrier, and form adsorbed CO2. CO2 doesn't bind much more strongly, so the energy of CO2 adsorbed to the catalyst is only slightly more negative than CO2 gas. That's because CO2 is very stable. It doesn't really need to adsorb to anything to make it happy. So it, will do that, but it doesn't need to. So it's pretty easy once formed to get that CO2 off the surface. So this is what this would look like in the in a heterogeneously catalyzed reaction. One thing to note here, what we basically did do is molecular oxygen doesn't dissociate in the gas phase. Well, it could. We'd have to, again, heat the temperature up really hot so that oxygen molecules literally vibrate apart. However, it will readily adsorb to this platinum catalyst. Oxygen loves to adsorb to a platinum catalyst. To get an oxygen molecule, it's going to bind to a platinum catalyst. I have a platinum ring. I'm not wearing it right now, but imagine imagine this silicon ring as a platinum ring. There would be oxygen molecules adsorbed to that, right? So oxygen likes to adsorb to a platinum surface, and once it adsorbs, it will pretty readily dissociate into oxygen atoms. So to break that oxygen-oxygen bond on a catalyst is significantly more facile than expecting oxygen to simply vibrate apart in the gas phase. Hence, the catalyst is providing a lower energy route from reactants to products, and what it's mainly doing there is dissociating that oxygen molecule.